Let us now talk about ramification. So first we will state an important theorem. So integral closure of a Dedekind domain is a Dedekind domain. So more precisely, so consider a Dedekind domain A, and this Dedekind domain A has field of fractions K. And now you can consider a finite separable extension of K. So this is L, which is a finite separable extension of K, and let B, this B is integral closure of A in this finite separable extension L over K. So then B is a Dedekind domain. So B is integral closure of A in some extension L of a field of fractions K of A, and we are saying this is integral closure of A, and therefore this is a Dedekind domain. So integral closure of a Dedekind domain is a Dedekind domain. So this theorem actually requires theory of discriminants to prove this result, and discriminants are extremely important in computational algebraic number theory. So we will not prove this theorem, but we will study ramification using this theorem. So consider this P a prime ideal in A. So then you can consider extension of P in B, because P is integral closure of A, so it contains A. So now you consider this extension, and this prime ideal, say, factorizes like this, because B is a Dedekind domain, so this will factorize like this, where each of these EIs is greater or equal to 1. So these capital P's, these are prime ideals lying in this B, and this B is an ideal in A. So this P is prime. So this P is ramified in B if any of these EIs is greater than 1. So you have factorized it into this bunch of prime ideals, and if any of these EIs here is greater than 1, then we will say P is ramified in B, and this is called the ramification index. So for every this big prime ideal, you have a corresponding ramification index. So if Pi is in the factorization of P, we say Pi divides P. So Pi divides P. And the corresponding ramification index, you can write it as E Pi over P, or you can write it as EI like this. So now we can consider field extension. So these lies within B, and this P lies within A. So you have an extension like this. So say Pi divides P, so you can have an extension like this. So this is our field extension. Now corresponding to this extension, you can have the degree. So your degree of this field extension you denote by F Pi over P. So this is called the residue class degree. Now if this EI is 1 and this residue class degree is also 1, so this you can again call as Fi. So if EI is 1 and Fi is also 1, so EI corresponds to this ramification here, ramification index. So this is 1 and this residue class degree is 1. Then the prime is said to be split in B. If you just have one factor here, so not a bunch of factors, just one factor, so there R is just 1, and this the index here EI is also 1, so you just have one factor here, then this prime P is said to be inert. So let us see some examples. So you set A as integers and set K as Q. So obviously if A is integers, then K is its field of fractions, so it is rationals. So now we have to have a finite separable extension L. You set L as this complex I, you are adjoining it to rationals. Then we have to talk about integral closure of integers in this, and that is just this B. So this is integral closure of integers in this thing. So this is this complex I attached to integers. So now this 2 here, which is a prime number in integers, this will factorized as 1 plus I square in here zi. So ramification index is 2, and this is the corresponding prime ideal here. 5 will split as 2 plus I times 2 minus I. So notice that power is 1 here. So this EI is 1. Actually, if you start computing corresponding this degree of extension, that will also be 1. So you will have to compute 2 degrees of extension. So 1 would be corresponding. So this A modulo P would be Z modulo 5, and then this P modulo Pi would be Zi modulo this. So you will see that the degree of extension is 1 for this 2 plus I and 2 minus I. So this splits, and 3 is inert. So because 3 will just factorize as 3 itself. So E would be 1 and R is 1. So P here, which is 3, will be inert. So now let us give a geometric interpretation of ramification. So say you have this morphism between curves C1 and C2. So this is a non-constant map of smooth curves. So both C1 and C2 are smooth. Now we have seen in algebraic geometry that such a map will give rise to this contravariance. So attached to C2 you have this field, and attached to C1 you have this field. So coordinate rings and their field of fractions. So this is field of fractions of the corresponding coordinate ring of C2. This is field of fractions for corresponding coordinate ring of C1. So this gives rise to extensions. So this KC2 goes into KC1. You have this extension. So again arising from the contravariance, this phi star going from KC2 to KC1. So this is our standard algebraic geometry argument. So now consider some point P on the curve C1, and the image of point P is Q on curve C2. So let us draw. So say this is our curve C1, and this is our curve C2, and you have this map phi. So what is happening is you have some point P here which gets mapped to point Q here. Now there are other points also. So say there is a point P2 here which also gets mapped to Q, and there is some other point here which also gets mapped to Q. But we are just worried about this particular point P right now. So we are just considering this point P which is getting mapped to Q here. So we are saying phi of P is Q, a point of curve 2. So this is the map, and we said we have the corresponding map in the opposite direction, which takes this KC2 to KC1. So this field is the field of fractions of the coordinate ring corresponding to the curve 2, and this is the field of fractions corresponding to the coordinate ring of this curve. So you have this. So now at this point Q sits a discrete valuation ring. So there is a DVR, or a discrete valuation ring, sitting here. So every time you have a discrete valuation ring, you know that it is generated by a uniformizing parameter, say pi. So you can talk about order of elements in this discrete valuation ring. So that is just the order of this pi in this valuation ring. So at Q sits a discrete valuation ring with uniformizing parameter pi, which lies obviously in the field of fractions here. Now you can shift this pi. So this pi lives here. You can apply phi star to it, and you can shift it here. So this becomes phi star of pi. So you can shift this to this, and now this is here. So you can talk about what is the order of this function on the discrete valuation ring sitting here. So we have a DVR, a discrete valuation ring, sitting here, and we have a DVR, which is a discrete valuation ring, sitting here. So what we are saying is you're taking the uniformizing parameter here, pushing it here, and then since there is a discrete valuation ring at this point P, you can talk about order of this element here. So we can shift this to a discrete valuation ring sitting at P using this function, and then we can define ramification index of phi at point P. So this is defined at E you denote it by E phi p. So this is just order of phi star of pi. So if you know about discrete valuation rings, you exactly know what the order is. It's just power of the uniformizing parameter here, which will appear in this function. So say our uniformizing parameter is t here. So this is always greater or equal to 1. So phi is unramified at point P if this is 1, and it is unramified if it is unramified at every point of C1. So you can talk about unramified at a point P or unramified in general. If you just say phi is unramified, that means it is unramified at every point of curve 1. So this is a ramification for curves, or you can say Riemann surfaces.